soft metals that explode on contact with water, ice that burns, air that turns toxic, and chemicals so unstable they can easily detonate. These are chemicals scientists discovered that should not exist. So there's this soft metal called sodium that you can literally cut with a butter knife. It looks harmless, like a dull gray rock, but drop into water and you get violent explosions, flames shooting across the surface. Sometimes the whole thing just detonates. Early chemists were completely blindsided by this. I mean, they figured water was about as harmless as it gets, right? But mix it with sodium and suddenly you've got fire and explosions, apparently. The reaction is so violent because sodium really wants to grab oxygen from the water molecules. And when it does, it releases hydrogen gas that immediately ignites. The whole process happens in seconds. Now, sodium is actually in table salt, which you can dissolve in water all day, no problem. But pure sodium, absolutely not. It has to be stored in oil because even the moisture in regular air can make it react. Scientists eventually figured out the chemistry behind this, but I mean, imagine being the first person to try this in 1807. Your name would have been Sir Humphrey Davy, who was a British chemist and inventor. Normal oxygen is 2 atoms stuck together, which is what we breathe. Ozone is 3 oxygen atoms in a molecule. That one extra atom, it changes everything. It's toxic to breathe, super reactive, and has this sharp smell that you can sometimes notice after lightning strikes. But despite being toxic and unstable, we need ozone to survive. There's a layer of it, of course, way up in the atmosphere that blocks ultraviolet radiation from the sun. Without it, we'd all be getting fried by UV rays constantly. So the same molecule that would poison you if you breathed it down here is protecting you from space radiation up there. The weird part is that it's the exact same element as regular oxygen, just arranged differently. Same atoms, completely different behavior. Ozone breaks down pretty quickly back into regular oxygen, which is why it doesn't stick around long in the lower atmosphere. It's unstable by nature. Most people know mercury as a liquid metal. There are other alloys that'll melt right in your hand from body heat alone. Gallium and indium can be mixed together to create a liquid metal that looks solid at room temperature, but then just liquefies when you hold it. I mean, the T-1000 from Terminator had to have been heavily inspired by this. It's a regular looking metal that turns into what looks like spilled water. It freaks people out because metal is supposed to be solid. That's the whole point of metal. You use it for tools, for things that need to stay rigid. Solid metal shapes like knives and stabbing weapons. But you can pour these liquid metals. They still have that shiny metallic look. The reason this happens is that these metals have really low melting points. Gallium melts at about 85 degrees Fahrenheit, which is below human body temperature. So when you hold it, your hand is hot enough to turn it to liquid. When scientists analyzed the Murchison meteorite that landed in Australia back in 1969, they found amino acids inside it. These are the building blocks of proteins, the kind of molecules we associate with living things. Except this rock came from space and never had any life on it. This was quite the discovery because it meant complex organic chemistry can happen naturally in space without any biology involved. These molecules formed out there in the void, probably in clouds of dust and gas, through basic chemical reactions. But this means if life's building blocks are, floating around in meteorites, then the ingredients for life might be way more common in the universe than we thought. Maybe life here on Earth actually started because of stuff carried over in space rocks. And of course, life might be able to start in places we never expected. We all pretty much assume at this point that there must be some form of alien life out there in space, but stuff like this makes the probability even higher. Under normal conditions, oxygen is a gas. That's all we've ever experienced. But if you crank up the pressure to extreme levels and drop the temperature way down, oxygen becomes a solid. It also becomes magnetic. This shocked scientists because oxygen in the air doesn't have any magnetic properties at all, but compress it and cool it down enough, suddenly it starts responding to magnets. You can actually see chunks of solid oxygen being attracted to a magnetic field, which looks completely wrong because you're watching the air you breathe behave like a solid object. The science behind it has to do with how oxygen molecules align when they're packed together under pressure. The magnetic properties come from unpaired electrons in the molecules that line up in certain ways when the oxygen is in this solid state. But knowing the explanation doesn't make it any less weird to see. This is usually demonstrated with liquid oxygen though, so let's take a look at that. Water freezes at 32 degrees Fahrenheit or 0 degrees Celsius, but if you cool it down very slowly and keep it perfectly still, you can get water to stay liquid well below freezing. The second you disturb it, tap the container, drop something in it, even just vibrate it slightly, the whole thing will freeze. You can watch it happen in real time. The ice kind of spreads through the water like a shock wave. And with within seconds, the whole thing is solid. It's really cool to watch. This happens because the water molecules need something to trigger crystallization. Water is pure and undisturbed. The molecules don't have a good starting point to form ice crystals. They're stuck in this weird state. They're cold enough to be solid, but haven't actually made the transition yet. Any little bump gives them that starting point, and boom, you got ice. You can actually do this at home with bottled water in a freezer if you're careful enough. By careful, just don't drink the super cold water because it'll freeze inside you. Next up, we have azidoazide azide. This chemical is a disaster waiting to happen at all times. It's made up of nitrogen atoms loosely connected to each other. Every single one of those connections wants to break apart and release energy. Moving it makes it explode. Touching it makes it explode. Light makes it explode. Leaving it completely alone in a dark room, that also will make it explode. German researchers created this stuff in 2011. Their own report basically said they couldn't measure how sensitive it was because every time they tried to test it, it just blew up. They put it in a spectrometer to study it, turned on the laser, and it detonated inside the machine multiple times. They kept trying and it kept exploding. The compound is nearly 90% nitrogen by weight, and nitrogen atoms desperately want to bond together in stable pairs. When they do that, they release a massive amount of energy. So azidoazide azide is basically pure stored energy that's constantly on the verge of releasing all at once. It has no practical use because you can't safely handle it, transport it. Hell, you can't even store it without it exploding. It exists purely as a weird little curiosity in a lab setting. So, if there's a hall of fame of chemicals that shouldn't exist, this one definitely should be included in there. Teflon was a complete accident. A scientist in 1938 was trying to make a new refrigerant gas, so basically trying to make a chemical to help fridges run better. But instead, he created this white, waxy substance that turned out to be one of the most unreactive materials ever discovered. Almost nothing sticks to it. Almost nothing breaks it down. Acids don't touch it. Extreme heat barely affects it. And it's kind of the opposite of the last entry on the list. It's bizarre because most materials react with something. You can dissolve plastic, metals will corrode, even glass will slowly break down over time. Teflon basically doesn't react with anything under normal conditions. That's why it's perfect for non-stick pans. Food can't stick because nothing can form a chemical bond with the surface. Nature doesn't usually make materials this unreactive. Things are supposed to break down over time, corrode and degrade. Teflon just doesn't, at least not on its own. Throw it in a fire and it will break down. Picture regular ice. Now picture that ice catching on fire and burning like a candle. It seems pretty weird, but this does exist. It's called methane hydrate or fire ice. It looks like white ice, feels like ice, but if you hold a match to it, it lights up and burns with a steady flame while water drips off it. The stuff forms naturally on the ocean floor and in frozen ground where methane gas gets trapped inside ice. The water makes a kind of cave and the methane just sits in the spaces. There's a huge amount of it all over the world, way more energy stored in methane hydrate than in all regular oil and gas reserves combined. Countries like Japan and China are researching how to extract this as an energy source, but it's tricky because the methane is only stable under specific pressure and temperatures. Change those conditions and it just releases all the gas at once, which could be really bad for the environment, since methane is a powerful greenhouse gas. Nitroglycerin looks like pale yellow syrup. It pours like oil, but it could detonate at any moment from the slightest shock or vibration. When this was first synthesized in 1847, chemists were blown away, sometimes literally blown away. They couldn't figure out how a substance that looks so harmless could be so devastatingly powerful. It's not just that it explodes, it's that it doesn't need much of a trigger. You drop the container, it explodes. Let it get too warm, it explodes. Jostle it while transporting it, it explodes. Early shipments of nitroglycerin had a habit of randomly detonating and killing everyone nearby. The molecules are packed with nitrogen and oxygen atoms arranged in a way that they want to break apart and form more stable compounds. When that happens, it releases a huge amount of energy in a fraction of a second. The pure liquid form was so dangerous that it led to laws banning it being transported. Alfred Nobel eventually stabilized it by mixing it with an absorbent material to create dynamite, which was way safer to handle, still incredibly powerful, of course. Explosives are supposed to be, powders or crystals, something clearly dangerous looking. Nitroglycerin is a liquid. You could put it in a bottle, it would look like cooking oil sitting on a shelf. Very dangerous stuff. That's been the video for today, and I will catch you, yes, you specifically, in the next one.